Hey guys! So, gonna go over some kidney stuff, tubule issues in particular, and some basic kidney anatomy, and then diseases that lead to it. So, kidney anatomy, things that will break kidney anatomy, and what happens. So, let's go ahead and get started. First, we have the blood vessels leading to the kidney, and we have afferent and efferent kidney tubules once you're in the kidney. And so that means in between those, clearly we have a glomerulus, okay? So this is my representation of a glomerulus. And the glomerulus is going to filter some things out, and those are going to go into the proximal tubule and the loop of Henle and the distal tubule. Proximal, loop of Henle, distal. And then that'll go out in the nephrons and renal pelvis eventually, and then to the bladder, and then out the urethra and out of the body. So, proximal tubule, distal tubule, loop of Henle. Okay? I'm going to draw just a little line here and a little line here because they have different jobs. So this guy's job is to reabsorb stuff. And when I say stuff, it means glucose, amino acids, ions such as sodium in particular is what we're going to be looking at today. Okay? And bicarb. So these first three, it's going to, glucose and amino acids rather, it's going to absorb basically 100%. Glucose and amino acids all should be reabsorbed. Bicarb is going to be 90%. And so you leave a little bit of bicarb in the urine, and that affects pH and whatnot, and you'll absorb the other 10% or however much of it you want to reabsorb in the distal tubule. All right, so proximal tubule, the easy way to think about it, you are going to reabsorb important stuff, okay? And that's really pretty good for diseases. Now, moving from there, what happens then if your proximal tubules get damaged? This just means that the tubule is broken, okay? Tubule broken. It cannot save all of these things. It cannot save the glucose, the amino acids, the ions, especially sodium, or the bicarb. And so all of those things that are supposed to be rescued and put back in the blood just flow through, and they would be peed out, and they would be gone. Now, that's really unfortunate because we need sodium, and we need to keep our negatively charged bicarb. Bicarb is an anion. It has a negative charge, and we have an anion gap that we have to preserve. Bicarb also affects the acidity and alkalinity, the pH of the blood, of course. All right, so I'm going to go ahead and circle here the two really important guys, sodium and bicarb. All right, and I'm actually going to circle bicarb with a different color here because we're going to make two different pairs. Bicarb. All right, so we have two important guys going out. Now, how are we going to fix that? Our proximal tubule is down, but we don't want to die, so let's do something. All right, so the body says sodium. We can save sodium. We have a backup system in the distal tubule. We have two backup systems. Backup system for sodium is, hey, let's pump sodium in the blood, but over here it costs us a potassium from the blood. So we gain sodium and we lose potassium. Okay? Gain sodium, lose potassium. I'm going to go ahead and put that into a better color so that it's easier for you guys to see. Gain sodium, lose potassium. Potassium goes into the urine. So this would make so that our blood then has low potassium, and it has okay amounts of sodium. It might still be a little low, but it's not a lot low anymore because we saved a whole bunch. Okay? I'm going to circle this in red because the problem down here that we circled in red was sodium. Now we're solving the sodium in another circle of red. So that's the first pair. Save save sodium. All right, job number 1. Job number 2 is save the anion gap. And so that means we have to have a negative charge. All right, so bicarb does not have a really great way to be reabsorbed. If we could, we would. We can't. And so we've got the sodium pair, but what do we do about the bicarb? Well, if we can't get bicarb, let's just get some other ion that we are good at saving, some other anion that's a negative charge. And we would do that by saving chloride. We are good at saving chloride. So we will go ahead and save chloride and move that into the blood. And then we have way more chloride than normal because we have to replace all the bicarb that has been lost. And so we end up with hyperchloremia. Hyper, lots, chlor for chloride, emia, in the blood. Lots of chloride in the blood. So this is going to be hyperchloremia, but we have fixed the bicarb problem. So blue circle, so that's 2 pairs. First we have the red color problem, and then we have the blue color problem, and those are 2 pairs. Sodium lost here, sodium saved here at the expense of the potassium. Bicarb lost here, at least we get an anion back to preserve the anion gap right here with chloride. And that is, in a nutshell, the physiology of when it's working, we save everything. When it's broken, we use our second chance to pull back what we can. And then, since we've lost bicarb, we're going to have acidic blood. And this will be metabolic acidosis. But at least we don't have an anion gap. So if you want to, go ahead and pause. What was the first pair? And what was the cost, which is the ion that we have to pay to save the sodium. And then what was the second pair? And how does the blood end up, and what do we have high in the blood, and what's the condition of the blood? Okay, so hopefully you went over that in your head. And once again, we lose sodium, we save it at the expense of potassium. We lose bicarb, we save chloride in its place to preserve the anion gap, but because we still don't get bicarb back, it's still acidic blood, metabolic acidosis. Okay, so that's general pathophys for when you have proximal tubule issues. Now, what are issues? Moving to the second part. So all that's first part. Now we're moving to the second part, and that's going to be diseases. Okay? Diseases that can cause proximal tubule issues. So over here, we're going to go ahead and make a little box for diseases, just because it's separate. And we have primary kidney diseases, which I'm going to put just a first degree kidney tubule, I should say. Diseases and secondary. So primary means that it's inside the kidney's fault kind of a thing. The kidney itself is damaged. Secondary is outside influence causing an issue that's overwhelming the kidney. So primary, we have 3 that were mentioned and 1 that was gone into in detail. So the first one is Wilson's, okay? So Wilson, how many of you have seen, I think it's, there's a volleyball named Wilson, right? And there's a movie, Castaway, that's what it is. And there's a volleyball, and his name is Wilson. So I'm just sticking a volleyball here. If you like pictures, enjoy it. If you don't, close your eyes. So in Wilson's disease, we have 3, so that's just a volleyball. We have copper issues, all right? We're not very good at using copper transport, and we're going to have issues in the liver. And for this is just, I'm going to have a person here. Imagine a person that is better drawn than this for your mental memory. But we're going to have problems going from the bottom to the top to the front. Okay, so we have the liver being the first problem in Wilson's, copper issues. And this volleyball I see is copper plated, but anyway, continuing on. Liver, then we're going to have neurological issues. So I see that in the back of the head, cortex. And then in the eyeball at the same time. So you have the liver first, and then you have back of the head and front of the head. And so cerebral cortex and Kaiser-Fleischer rings. Okay, and that's when you see this like gold coppery type ring around and through the iris. Okay, and so that's Wilson's disease. Basically, if you have jacked up copper processing, you will see those three things: liver and cerebral cortex, and then eye. Kaiser-Fleischer rings. Kaiser-Fleischer rings. All right, and the copper jacking up everything and the cells being damaged will send damaged cell tissue and copper through the glomerulus, and then that will damage the tubule, and then you'll lose all of these ions, and we'll have this happen because of Wilson's, and because the tubule itself is now damaged. Next, we have, and that's the one that she went into more detail on. Next, we have cystinosis, and that's when you have cysteine, which is an amino acid, and you have a whole bunch of lysosomes. You have cysteine balls, and lysosomes can't break down a substance that leads to a buildup of cysteine balls. And so the lysosome will throw these cysteine deposits out into the cysteine crystal into the blood, and then that goes into the kidney, and then they deposit into the tubule area, and that causes damage. And that's as much as we're expected to know, is that cystinosis will lead to cysteine deposits in the proximal tubule, and that will be damaged. So cystinosis. All right, and then this one was Wilson's. Third primary disease that she mentioned was glycogenosis, which is going to be lots of glycogen, and I presume that glycogen, which is all branching, if you recall, and so that's just what I drew, was a bunch of branching links of glucose. All right, and so we have a branch coming off there. Anyway, this is just glycogenosis. And at this point, I would review going, what's Wilson's? How does it develop? What is cystinosis and the deposits? Where do they deposit? What does it damage? And then glycogenosis, honestly, all I know is that it damages right there. I don't recall that she went into any more detail. Like I said, mostly Wilson's was what was gone into. I would go ahead and review those three as diseases and go ahead and pause. All right, so if you chose to pause, hopefully that went well. Next, we have second degree. Second degree, the main one was lead, which is abbreviated PB, and other toxins. And so I'm just going to, toxins in parentheses over here. Lead has a unique characteristic in that children absorb it way better than adults. This is probably because children need a whole lot of divalent minerals like calcium and iron because they're growing. And so that means that they're going to be bringing those in, and if lead is present, it uses the same transporter as we learned in nutrition, so it'll bring lead in as well. And so kids will absorb up to 50% of lead that they eat. 50%, whereas adults who don't need as much of the divalent minerals because we're not like, growing as much, we do 1/10 of that, 5%, okay? And the lead, if you absorb it, it will damage the tubules, but not in a way where there's any like permanent deposits and the kidney itself is having an issue. So that's why this one's second degree, and the other ones actually have deposits of either the copper or the cystinosis or the glycogen that stays there and then inside the kidney you have damage, whereas this is just something coming in from the outside and damaging it as it goes by. So deposits fly by. That's my understanding. Hopefully it helps. All right, so, and I wrote 50% and 5% here because I'm pretty sure you can't read everything. Moving from there, I would say one other thing. Once you have these diseases and you have damage, you are going to find in the urine a couple markers that she mentioned. And these markers are, number one, beta microglobulin. Microglobulin, which should not be in the urine. If it is in the urine, that means we have a tubule disease. Okay, and it could be proximal tubule, it could be all tubules. Either way, this is kind of a general one, which is why, yeah. So then we also have retinol binding protein, BP. And if you remember, retinol is a version of vitamin A. Retinol is the one that goes through the blood, and so we want to have a binding protein to hold that version of vitamin A. Turns out that that is a protein that will leak through because the tubules can't rescue it, and it's easy to use as a marker. And so we have beta microglobulin and retinol binding protein. And those are two proteins that should not come out, and if they do, we know that we have tubule damage. Okay, so that wraps up part one, basic physiology, basic pathophysiology, and part two, diseases, and then a little bit of detecting diseases. The last thing that I'll say is some general things that will damage just in general, the whole tubule system, the glomerulus, etc. High blood sugar, so diabetes, can give you issues. Toxins can give you issues. It's pretty self-explanatory. Basically, anything that will wear and tear on the bloodstream will also wear and tear on the glomerulus and the tubules. Now, one thing to remember in this third part of general is if you actually break in a general way, you will break these second chance rescuers of sodium and of chloride for the anion gap and for keeping sodium in the blood. And so what does that mean? It means that this is gone. And so we actually do lose all that chloride, all that sodium. And those just go out in the urine and they don't get saved. And so if you have a lot of toxins, diabetes, general tubular damage, then you are going to have hypernatremic urine and a lot of urine, and your potassium in the blood would stay normal, or at least it wouldn't be as low. You would have hyperkalemic acidemia again because you can't save the sodium. And so the potassium stays in the blood now, and now all of a sudden it's high potassium and it's acidic again because that little rescue operation can't happen. Hopefully that makes sense. All right. So yeah, that's general tubular disease. All right, well, I hope that helps. Part 1, Part 2, Part 3, and I'll get out of the way so that you can see everything and catch you next time.